Alright, so this is another technique. Let us discuss this. Very simple one actually. Just like DH, we had not much of an issue with DH. Same way, Elgamal cryptographic system is also like that only, because this also uses the discrete logarithm process. That means it also uses a trapdoor function, which means that one-way traffic, one-way movement is easy, but decrypting it, or rather deciphering it, will be always difficult if you don't know the private key. So the same principle applies over here, except for some new forms, very small changes. So if you observe the first thing, so first of all, we need to choose a Q, which is a prime number, like in case of, you can relate to very easily to DH. So you need to have a Q which will be sufficiently large. That's one of the conditions of Elgamal. Alright, please concentrate on this. Okay, it's very simple, but again, if you don't recollect the process, it will be difficult. So you have this Q, which will be a prime number, but a relatively high prime number. The advantage of this is that you don't need that P comma Q. Remember, in case of DH, we had to make two factors. Here, the factors are not there. Only the prime number is sufficient. So you have the Q over here, and alpha is the primitive root, just like we had it for the DH also. So the primitive root is given by alpha, and the same manner we have XA, which is nothing but the private key. You can see over here, XA is the private key. Sometime in this Elgamal, what happens, we say this alpha, the primitive roots, as the generator. We sometimes call it this way. So suppose in your question paper, sometime it comes as generator. Generator is synonymous to the primitive roots. So please make a note of it. Okay, because mostly it is like varying in different books in different way, but ideally the same thing. So you have a prime number over here, Q, you have a generator over here, and based on the generator, you are generating a public key, which is YA. So that's the public key over here, as same as that of the previous process of DH, right? So now, naturally, this is the transmitter side. So the transmitter is sending all this information via the public channel. So everyone is getting hold of those public information. Okay. Now, the encryption process. Now what happens again, the same way, it will select an M which will be less than or equal to Q minus 1. So this is my condition of the message. Just like we had it for Elgamal, the same thing. Okay. And let us choose some kind of a random integer small k. This is where it gets different from that of the DH process. So this small k that you are looking at, that has also a range which will be ranging between 1 to Q minus 1. Alright. And based on this small k, we are going to find out another set of key which is capital K over here. And that is given by the public key YA. Please make a note, YA whole to the power small k, this is small k, mod of Q. Alright, so that's how it should be. Now, this capital K that you are looking at, based on this capital K, alright, based on this capital K, we are going to encrypt the data. Now, encryption is in the left hand side, that is in the transmitter. So if you observe, there are two parts of the ciphertext. Unlike to DH, where there was only C, here we have C1 and C2. Two parts of it will be generated. So C1 will be encrypted in the manner alpha to the power K, small k, that is mentioned over here, that small k over here. And C2 will be capital K multiplied by the message mod of Q. So please remember this important step. The step that you are observing over here, this is very important because this happens to be the major difference of Elgamal compared to DH. In case of Elgamal, in case of DH, we only had P we got a mod of something like that. What is now? So here what is happening, we have breaking up the ciphertext of the same message into two halves. There is a reason for it. You will soon find that at the decryption how it happens, then only you will understand this. So, yes, please. So, no, this is small k actually. This is step 5. This is a typographical error. This should be small k actually. That's why I mentioned steps 5. So step 5 is the small key. Small key actually. Small key is a random key for which, with respect to which we are generating another key, capital K. So small k and capital K. Now we have two set of keys which are being used to generate two set of ciphertext in two different equations. Now what happens? Now we come the recovery time. We call it the recovery time or the decryption, whatever you call it. So now what will happen? That K prime will be C1 to the power XA. Remember, XA was the private key. So this is at the receiver end. The receiver where you have sent the message, he must be having or he or she must be having that particular private key. That's quite the obvious choice or obvious reason for which you are making this cryptographic solution. So definitely you will have the private key over here. So the C1 will be used with respect to XA and we will generate some kind of a K prime. This K prime is to be used over here. See this step very carefully. We have generated C1 and C2. C1 and C2. Now the C1 part is used with respect to XA, the existing private key, and we generate some kind of another key which is K prime. This is happening at the receiver. Alright? Now this K prime now being used over here in terms of its inverse. You have to take the multiplicative inverse of K. So that inverse is showing over here. So and the C2 gets multiplied. The C2 is over here. So that gets multiplied over here. And finally this M prime should be equal to M. So the two steps wise, the C1, C2 which is generated using K1 and K2 makes sure that the middleman attack that was there in Diffie-Hellman is sufficiently reduced. Remember the middleman attack that I told you in last class before we ended our CAT 2 syllabus. That if someone is in between middle, he or she can interpret the data and can find out or rather can try to mimic that he is the transmitter or he is the receiver like that. So that part can be significantly removed while using the Elgamal system. So what happens here, you can observe. So the steps, if I go back once again, we start off with generating or selecting a very high or a big prime number. Based on that prime number, we find out the public key which is YA based on the similar kind of equation as that of DH. And then we found out and then we send the data over the air. But before sending it, what we have to do is, we have to generate two sets of keys, two more sets of keys. One is the small k and the other one is the capital K. We using the small k and capital K, we are generating two sets of ciphertext, C1 and C2. And finally, we are receiving this, sending this over the air. And then finally, at the receiving time, we are utilizing both the C1, C2 and the small k and K prime. And we are using the private key over here as XA. And we are just getting back the data once again. Okay, so that's basically these last 4 lines are the changes that needs to be made in case of Elgamal. Let's take an example to understand that. Suppose this is the question where Q is given as 19. Naturally, you can imagine if Q is much bigger, the problems or the solution will be much longer as well as it will be more complex. So we are not going into that. So suppose Q is equal to 19. Now, these are the primitive roots which are possible for 19. But we can choose any primitive root in between. So, for example, in this particular case, we have chosen alpha equals to 10. Alright, so this satisfies the condition. And we have chosen XA which is equal to 5 because that also has a condition that private key should be within Q minus 1. Like the previous page it was there. So YA we are getting as 3 by substituting in the equation. Alright. So this is my alpha. What was the equation? Alpha to the power XA mod of Q. So that was the equation. So we are just substituting over here and we are getting the public key over here. So what we have right now, private key is this, which will be used at the receiver side. We have 19 as the primitive, as the prime number. Generator is given by 10 and the public key is given as 3. Okay. Now, let M is equal to 17. As again the same way, it should be belonging within, because Q was 19, so we have chosen 17. It's not that you cannot choose anything else. You can choose anything, but make sure the range is finite and maximally whatever we can do it. We could have chosen 18 also. Okay, but 19 minus 18, 18 we haven't chosen. That's just a example. That's why. So you have m equal to 17 and we choose k, small k is equal to 6 because the k condition was also the same. That's why the condition is not that difficult to memorize. They are all the same almost everywhere. So 1 to q minus 1, that's the condition. So k, the small k is chosen as 6. So we substitute over here, we get the capital K, which is coming as 7. Okay? Now we calculate C1 and C2. The formulas are given by alpha to the power k mod q. Same thing, we have just substituted. This calculation, I think all of you by now are familiar with it, and the answer will get as 11. And for C2, here again the same way we are doing, k is equal to 7 and m is equal to 17. So we have substituted those two, mod of 19. So 119 mod of 19, answer is 15, answer is 5. So your ciphertext C1, C2 is coming as 11,5. That's the generation part, encryption part. Any doubt here? Alright. Now the decryption, same way, just the reverse. So we have to generate k prime. So k prime is given by C1 to the power xa mod of q. Substituted over here, we get a 7. And we get the next one. We use the 7 and its inverse. 7 inverse of it. And we use the, you can see, remember the process I told you over here. And we get a value of 11 back. So this is my k prime. We substitute in the last equation. So C2 is given by, C2 was 5. So 5 multiplied by k inverse mod of 19 and we get the 17 as the message. So my m was 17. My m prime is also 17. Hence the key has been exchanged or the data has been exchanged from one transmitter to receiver using the Elgamel technique and using the small k and capital K elements. Same process can be applicable to any sort of question. Given here you can see that this is simpler because you don't need the factors for that matter. Only the primitive roots which will be relatable to generator and you will need a prime number. Alright. And you need the private key you can choose within the range, anything you feel like. So anyone is intruding on it, they can't be able to guess it because they don't have the private key first. Secondly, they will only get a part of the ciphertext. The C1, C2 makes it like part of the data is known, like part of the data is 11. It's not that the complete text is you are encrypting on the go. So that in fact is an added advantage for the security purpose as well. Alright. So this is again a continuity to the, I told you in the last class also, we could have finished it there itself. But since the time was not there and as we chose not to have this in our syllabus, I opted out on that day. So this is about the DH key exchange as well as the Elgamal. We also have another one which is usually the process which is done in elliptical curve arithmetic, which we have done in CAT 2. We will see how that elliptical curve arithmetic will be used for the encryption as well. That time in second module, we had discussed the arithmetic of it. The question in the first module, the first part of this CAT 2 question also I told you. Now we will see that how that particular arithmetic or the set of data that we are getting can be used for the encryption as well. Alright, so that we will discuss on Friday's class. Alright, and then we'll move on to module number 5 to some key aspect of how the key can be managed. Now we know the key can be exchanged. After that, the key management will come. So that's what we are going to discuss.